So today we are starting double angle identities. Now a double angle identity is in a form where a trig function contains two angles added together. For example, I can write sine A plus B. So this is one type of double angle identity, right? So whenever you want to expand this will be in a format of sine A cos B plus cos A sine B. All right. So this is the first identity we have to learn. This is the first. And then if we have sine A minus B, then the identity will be sine A cos B minus cos A sine B. So it is easy to remember that whenever you have this plus sign over here, you will have a plus sign over here. And when you have a minus sign over here, you will have a minus sign over here. And you have to remember that in sine A plus B, the first part would be sine A and cos B. So all the angles will be interchanged, right? So here would be A and here would be B. Similarly, here would also be A and here would be B. But when the first one was sine A cos B, the second part would be cos A and sine B. And same goes here, sine A cos B and cos A sine B. But as here is a minus sign, you would have to put a minus sign over here. But this thing won't be true for cos. For cos, what will happen is cos A plus B will be written as cos A cos B. Alright? And then you will have to give a minus over here. So remember, whenever you have cos A plus something, you will have to put the opposite in the expansion. So it would be cos A cos B minus sine A sine B. Alright? And as you can understand that the next one would be basically the opposite. So if we write cos A minus B, then it will be cos A cos B plus sine A sine B. So to sum this up, you could have written this in one line as sine A plus minus B would be identical to sine A cos B plus minus cos A sine B. So it's basically saying that if you have a plus over here, then this would also be plus, and if you have a minus, then it would be minus. So you can also remember like that. And for cos, you can write cos A plus minus B would be cos A cos B, then minus plus sine A sine B. Alright? And now let's see the same thing for tan. Alright? So if we say that tan A plus B, if we say that it's tan A plus B, then the expansion would be tan A plus tan B and divided by 1 minus tan A tan B. So the way I remember is that if you expanded this, right, if you just took this thing individually, separately, like tan A and tan B, then you would put tan A and tan B here. And if there's a plus, the numerator will get a plus and the denominator will get the opposite one. So if here's a plus, the numerator gets the plus and the denominator gets the minus. And also you have to remember that whenever you have a minus sign over here instead of plus, the whole thing will be just reversed. So the plus will become minus and the minus will become plus. So if I write tan A minus B, I can write this as tan A minus tan B divided by 1 minus 1 plus tan A tan B. And that's quite it. These are the three double angle identities that you have to know for sine, cos and tan. And also if you extend this thing, all right, if you extend this part, you will get something you'll get a simplified version of some identities which you need for maybe integration or other stuff. So there are some more identities you need to know which can be derived from these identities we have just discussed. So the first one is sine 2a. Now you can write sine 2a as sine a plus a, right? And by using this one, using this identity, we can say that this is going to be sine a cos a plus cos a sine a. And as both of these terms are equal, you can write this as 2 sine a cos a. So hence finally we can conclude that sine a plus a, which is sine 2a, is going to be equal to this identity. And if you do the same thing for cos 2a, let's just do it. Let's say cos 2a, we can write this as cos a plus a. And if we now plug this in the formula or the identity, which is this one, we can write this as cos a times cos a and minus sine a times sine a. So this can be written as cos square a minus sine square a. And you can further simplify this into other forms also, but this is the main form you need to know, all right? But you could have also written like this. You could have written cos square a minus, and let's say we can write sine square a as 1 minus cos square a, right? Using the Pythagorean identity, we can say that this is equal to 1 minus cos square a. And if you simplify this further, you're going to get 2 cos square a minus 1. So you could have also written the same expression in this form. And if you took cos square a and replaced it with 1 minus sine square a, you would have gotten 1 minus 2 sine square a. So all these boxed identities, right? This one, and this one, all these are equivalent to this one. All right. So now lastly, if we look at tan, if we look at tan 2a, we can say that tan 2a is basically tan a plus a, which is tan a plus tan b divided by 1 minus tan a times tan a. And you can simplify this as you have to write this as a. You can simplify this as 2 tan a divided by 1 minus tan squared a. So this is another form you could have written. All right. So that's for it. Now that's for today. But one thing I just want to show you is that if you wanted to extend this expression further, for example, if we write that cos 2a, cos 2a is equals to 2 cos squared a minus 1. All right, we can write this. Now instead, if you were given cos a, all right, if you were given cos a, then you could have written this as 2 cos squared a by 2 minus 1. Now see, when there was 2a over here, all right, you wrote this as a. So what angle you have been provided will become half and will be replaced here. So when you are provided a, then this angle would be half of a, right? So no matter what angle you are given, you can just simply compare this pattern and you can do other identities as well. Now why is this useful? For example, you might be asked to integrate cosine a, all right? So you might be asked to integrate cosine squared a. So let's say you were given to integrate cos squared a with respect to a. Now you wouldn't be able to do that directly because this is a squared over here. This isn't linear trig function. So you had to use some identity to make it into a form that you can integrate, right? So what we can do is, let's say using this identity, if we make cos squared a as subject, we can write that cos squared a is equals to cos 2a plus 1. All right, we could have written that this is cos 2a plus 1 divided by 2. Now this one is this one can be easily integrated. So we could have simplified this into 1 by 2 cos 2a plus 1 by 2. Now if you integrate this, you can easily do that, and this would be nothing new. This would be your O levels knowledge. All right, so you could have easily solved this. So similarly, you can also use some other patterns with this, but just make sure that the angles over here remain consistent to the angles over here, right? So for example, if you have 2, you have to make sure that this will be half of 2. So if you have 3 over here, then here would be 3 by 2. So as you had 2a over here, this is 2a divided by 2, which is a. And same goes for this expression. So if you had sine 4a, you could have written this as, for example, if you had sine 4a, you could have written this as 2 sine 2a times cos 2a. And you could also prove this in a different way. For example, you could write sine 4a to be sine 2a plus 2a. And if you put this in the formula, you can write this as sine 2a cos 2a plus cos 2a sine 2a. And this can be simplified as 2 sine 2a cos 2a, right? So that's quite it for today, and hope we're going to do the graphs of these trig functions in the next class.